Allow Zoom meetings. Yes, allow access. Hello, hello. I'm just going to ask if anyone has any questions from 5.1a. And it's seeing as it's just noon, I'll give a minute or two for people to log in if they are logging in. And for those of you who are here with me and waiting, if you have any questions, just type them into the chat, which I need to pull up. There we go. Excellent. Just double checking as always. Can you hear me? Yes, excellent. Can you see my screen? Yes. 2 for 2. That's so good. All right. We'll give it another minute or so just to see if anybody else is logging on. And I'm really impatient. So we're going to get started. This is 5.1b. Okay. And if you do come up with questions to 5.1a that you want to ask along the way, please feel free to do so. That would be great. And so this is posted up there. Again, there is a filled in version, a fill in the blanks version, and an answer key. So you can choose whichever one of those you want to look at. When you come back, I will make printed copies for anyone who wants them. I might ask you over the weekend to figure out if you actually want them. If you've already printed them out, obviously, you don't need me to make a copy. But anyway, there we go. All right, using acid-base indicators. So one thing that we can do when we actually have some indicators is use 2 or more of them to find the pH range of a solution. So let's say that we have a solution that turns phenolphthalein pink and it turns indigo carmine blue. What is the possible range of this solution, pH range of this solution? So we know that phenolphthalein, it has turned it pink, which means that the pH has to be above 10, because that's how we read that. And indigo carmine is blue. So we are going to look at indigo carmine now. Here is indigo carmine. Indigo carmine is blue at a pH, of course, by coloring it yellow. Now I've made it green. So let's make it like that. There we go. It's blue. And so we know that the pH has to be above 10. And we know that the pH has to be below 11.4. And so the pH range then is between 10 and 11.4. There are 2 ways of writing this. You can either write it as pH is greater than 10.0 and less than 11.4, or you can write it as the pH is between 10.0 to 11.4. If you prefer, you could use the word 2 if you wanted to. That would also be fine. Now, sometimes I get questions from students. What do I do? Does it include the 10.0? Does it not include the 10.0? What about the 11.4? The answer is it just doesn't matter. I think we talked about this yesterday. Indicators are really, they're not super exact, telling the difference between a yellowy green and a slightly less yellowy green is very difficult. So because we're ballparking it anyway, you can use either of these two methods, and I don't really care what it's doing at exactly 10.0 or exactly 11.4. Okay, so don't worry whether you're including those. If in fact, if you wanted to say greater than or equal to, you could do that as well. I'm just not too concerned about it, okay? All right, there's a little blah blah up there, me going on and on about how I don't actually care, you know. Indigo carmine at pH 13, what color is it? Indigo carmine, is it yellow? Is it green? Don't worry about it, I won't ask you, it's a silly question. Okay. Finding the color, oh, are we going to have a lab on it or do we not have enough time? Is this on the indicators? Yeah, I would love to have a lab on it. If we don't have time, we could probably do it. I mean, it's a fun lab because you get to see all the colors. We could probably do it like on the last day of class and it would just sort of be for fun, and you wouldn't have to actually like do a write-up on it. Does that sound okay? Don't know. Okay, cool. All right, and why is my chat so big now? Let's throw that into the corner. There we go. All right. So we could also find the color of an indicator in various solutions. So if you are asked to find the color of an indicator, you need to find the pH. If you need asked to find the color, you need to find the pH. If they tell you the pH, that's really grand, it's super easy, but you know, maybe they don't. Maybe instead they give you the concentration of H+. Oh, well, this is pretty straightforward. We know how to find pH. If we have an H+, we take the negative log of the hydrogen ion concentration, just like that, and we get 10.72. And then we just go up to our chart and compare. Where is 10.72? It is above 5.4, so that's going to be blue. If we are told that the pOH is 7.8, well, again, we can't, these values right here are pHs. We can't work with pOH, so we need to change pOH into pH. And hopefully you know that pH is equal to the pKw minus pOH, because of course pKw is equal to pH plus pOH. Yes. And pKw, the value of pKw is 14. So that's going to be 14 minus the pOH 7.8 gives us 6.2. And now that we have 6.2, 6.2 slots in right. Oh, no, it's still blue. I don't know what I'm talking about. It's still blue, still above 5.4. I was getting excited that we would have a different color, but we don't. But here, ooh, look, and we don't have to calculate anything. We have a pH of 4, and pH of 4 slots into the middle here. And what color will it be at pH 4? Well, you're going to have a mixture of the yellow and the blue, so it is going to be green. Okay. Hopefully everything so far has been pretty straightforward, a little bit of reviewish kind of stuff. The next part is also just a little bit of review and applying what we already know and putting them together. If you are given the concentration of an acid solution, it's going to be important for you to know whether the acid is strong or weak, because if it is strong, finding the hydrogen ion concentration is really straightforward because it dissociates in a 1-to-1 fashion. All of the HX ends up getting used up, so we have none of that left, and we have all the H+, and so we know that those two are equal. The H+ is equal to the concentration of the strong acid. But If it's not a strong acid, if we have a weak acid, don't forget, we need to, if we have a weak acid, we need to use a rice table. Okay. What color is brom cresol green then? Brom cresol green in a solution of 0.025 molar sulfuric acid. Sulfuric acid is H2SO4. H2SO4, hopefully you remember, is a strong acid. Let's grab our acid table here. Sulfuric acid, H2SO4, is one of our strong ones up in this zone right here. Okay, so if it's strong, it dissociates completely. We have a one-way arrow. Oh, wrong button. There we go. So this is one of those ones where this dissociates and it gets all used up and it produces the exact same concentration of hydrogen. So we have none of this left. This is all gone. And all we have left is the H plus and the HSO4. And the reason I wanted to use this one as an example is that I wanted to remind you about diprotic acids. Okay, it is a diprotic acid. And only the first dissociation makes a significant contribution towards the hydrogen ion concentration. So even though you could have HSO4, 2-, further dissociating into H plus and SO4, 2-, these concentrations here are very, very tiny. And so they don't count for much of anything. Okay, so we only worry about, so we're like, this H plus is super insignificant compared to this H plus. This H plus is the important one. You know, maybe this one's going to end up being 0.00004. And you can see that that's much, much less than our 0.025. Okay, what do we need to do if we need to tell the color of brom cresol green? Well, we need to know the pH. We know the hydrogen. Simple, simple, negative log of hydrogen, negative log of 0.25, we get 1.60. Go back and consult the table again. Where did I put it? Oh, there it is. At 1.20, we're down in this range here, and so brom cresol green will be yellow. Oh, shouldn't it be SO4 3-? Let me just check. Oh, that's because I have mislabeled my HSO4. Thank you, Kyle. This is a typo. Well, it's probably not a typo. It's probably me just typing it wrong, which is different than a typo, which is where your finger messes up. So this should not be HSO4 2-. This should be HSO4-, which means that this would be HSO4-, which would mean that this one is actually correct. It was the other part of it that was wrong. Thank you for catching that. Okay. All right. What color is phenol red, chlorophenol red, in a solution of 0.5 molar HCN? Now remember, if you want to find the color of an indicator, you need to find the pH. And if you are given an acid, you need to ask, is the acid strong or weak? And it, in this case, is weak. We can go look that up if we want to. Got a booklet, cyanic acid, HCN. HCN, where are you? HCN, there it is. Okay, HCN. It's got a Ka of 4.9 times 10 to the minus 10. That'll probably be useful. Now, remember, and I got a little picture of this together for you. If you have forgotten if we have that weak little old lady, she's walking along carrying a bag of rice. So she's so weak that she drops the rice. Oh no, there it is all over the ground, and the crows come by and eat it and they yell, caw, caw. And that means that when we have a weak acid, we should use a rice table and Ka. I had far too much fun making that picture. Anywho, okay, so we're gonna use our rice table. I've just plopped it in here because I think you guys are pretty good at this by now, so you don't need to write it all down. So HCN dissociates. We are given 0.05 molar in our initial, in the question. And of course, at the beginning, there is none of it dissociated. We are trying to figure out the hydrogen ion concentration. So that's going to be our unknown. Okay, and CN, everything's 1 to 1 to 1 here. So the changes are all X, X, X. Don't forget, you guys were really pretty good about this from the quizzes I've read so far online. I'm not marking those ones. I'm just giving feedback. Well, I'm kind of marking it, but not really giving you. When you have it handed in, you'll get the answer key. That might happen tomorrow because I got more stuff happening this afternoon. Anyway, sorry, getting distracted. Okay, so we got our rice table, Ka. Plug everything in. We assumed X was insignificant, so we can just have the 0.50 there. And we solve for X. Okay, algebra happens. And X, of course, if we go back and we say, what is X? X is our hydrogen ion concentration there. All right. Now that we know hydrogen, negative log of hydrogen equals 5.31. And we say, what does that do for chlorophenol red? Well, that's in the middle of our transition zone. And so between the color change between yellow and red is, of course, orange. All right. Are we so far so good? Nobody's saying no. I'll take that as a yes. Okay. Now, if you're given the concentration of a base, you are also going to have to determine if it is strong or weak. But in this case, it's pretty straightforward because the strong bases are all going to be metal hydroxides. Okay. And they're going to be the ones where you see a metal attached to a hydroxide. Those are your strong bases. Your weak bases are going to be the ones that you would see on the right-hand side of the table here. We've got our bases, okay? And so our weak bases would be the ones in this section over here. These would be our weak bases all the way down, la, 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 et cetera, et cetera. But we don't know how to do calculations with weak bases yet. That'll be for tomorrow. So we're just going to leave weak bases alone for today. For today, we're just going to be looking at the strong bases because they're pretty straightforward. You're going to use the coefficients. So if you have a 2 here, that's going to produce 2 hydroxides. If you have two hydroxides, if there's no coefficient, or sorry, no subscript, well, just 1 hydroxide. Then you can find hydroxide using the coefficients. Then you can find either, you can go 2 ways on our little chart here. You can go, remember we got H plus here, OH minus here, we got pH and POH, and we can go from hydrogen, or sorry, if we have hydroxide, we can go to hydrogen, and then we can go to pH, or we can go from hydroxide to POH and then to pH. I think you guys are pretty good at that as well. But I've got it all shown here just in case there's been, you know, a little holiday brain happening. Okay, what color is thymol phthalate in 0.30 molar barium hydroxide? So we're going to want to write our dissociation. for barium hydroxide, so we can see the coefficient. And that gives us 2 hydroxides for every barium hydroxide that dissociates. And so if barium hydroxide is 0.30, then the hydroxide is going to be twice that much. It's going to be 0.60 molar. All right, and then you can do the standard calculations. Either find your hydrogen using, this is just a rearrangement of Kw equals H plus times OH minus. Rearrange it and solve for hydrogen. And if you now have the hydrogen, of course, you can negative log it and find the pH. Or, if you like, instead, you can take your hydroxide ion concentration, take the negative log of it, which will find you the pOH. And then we can take our formula, which is that the pKw is equal to pH plus pOH. We rearrange it to get that lovely one, which gives us 14 minus pOH 2.2 is 11.78. If you don't get the same answer going both ways, then you've done something wrong. Now, at 11.78, what is our color going to be? Well, that is above 10.6, so that is going to be blue. Okay, we are. And I'm just saying here, we will learn soon how to determine the pH of a weak base solution. So we're not going to worry about those right now. Okay, finding the color of a mixture of indicators. All right, so what color would a solution of pH 6.4 be if the following indicators are present? We have phenolphthalein. If you have your data booklet in front of you, you can go look up phenolphthalein, neutral red, and methyl red. That's phenolphthalein, neutral red, and methyl red. Ooh, wrong one. So our solution is pH 6.4. So for phenolphthalein, I'm realizing I should have put this in the document, but that's okay. So for phenolphthalein, 6.4 is down here below 8.2. So it's going to be colorless. Methyl red, there we are, 6.4. 6.4 is above 6.0, so it's going to be yellow. And our other one was neutral red, and it was 6.4. Oh, that's also below 6.4, so it's going to be red. So what we've got is we've got a mixture of yellow and red and colorless. What color will we get? Orange, yes. Okay, so this was colorless. This was, I can't remember which one was which. Neutral red was red and methyl red was yellow. Okay, neutral red was red, methyl red was yellow, and the solution will be orange. Okay, now, I think everything up till this point, probably straightforward, hopefully crossing fingers. This part is the only part that might be a little tricky. This is the lab that we will do if we have time at the end of the course. A lab is performed in which except for we'll do it with more indicators. A lab is performed in which 3 different indicators, HIN1, HIN2, and HIN3, 3 different indicators, are mixed in a spot plate. And if you don't remember what a spot plate is, it's like those ones that we used in the lab before Christmas, the ones that look like this. Yes. So in our spot plate, we are going to put some HCl, some NaOH, some HA1, some HA2. Oh, and I forgot I added an HA3, so let's add HA3 here. Yet another weak acid. And rather than me trying to cram them on this crappy little drawing of a spot plate here, you can imagine that this table now represents the spot plate. And so if I mix together HCl and HIN1, I get the color red. So HCl turns indicator 1 red. In another one, I put NaOH and it turns indicator 1 yellow. So what are the two colors of indicator 1? I'm just seeing if anyone's awake. What are the two colors of indicator 1? Together they make orange. The two species, though, we've got a red one and a yellow one. Okay. Now, why do I have it written like this, where I've got this sort of slash business here? You know, I've got HIN1 slash IN1 minus. Well, that's because, remember, all indicators are mixtures of a weak acid and its weak conjugate base. And that's why we have that mixture HIN1 slash IN1 minus. You'll also notice that all of these unknown weak acids, these are our unknown weak acids here. Those are our unknown weak acids, and they are also written as HA1 slash conjugate base, A1 minus. And that's because, guess what? They are also weak acids. And what do weak things do? They form an equilibrium. And what's going to be on the other side of the equilibrium from the acid form? It's going to be the base form. Okay, that's just what weak acids do. So that's why they're listed like they are. Now, our job is going to be to take these results and determine which acid is stronger than which other acid. And remember, we don't just have 3 weak acids, we also have our 3 indicator acids. So we actually have 6 acids in total. Okay, and we are going to put them in order from strongest to weakest using these results. All right. La 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 la. There we go. Okay, I've put this up at the top of the page again so that we can easily refer to it. So we can set up equations for what happens in each of the mixtures. So we are now going to take a look at this box here. Okay, we're mixing the HCl with the HIN1, and we end up seeing the color. I don't know why I didn't make it in red. We end up seeing the color red. That's really ugly. I shouldn't have done it that way. Here, hang on. That's somewhat better, still not great. That's all right. We're going to live with it. Okay, so we have mixed HCl and the indicator HIN1 slash IN minus. HCl is an acid. If it is an acid, it's not going to react with an acid. Acids react with bases. So it's going to react with the base form of HIN, which is IN1 minus. And so here we put those two together. We've put our acid together with our base, and we end up with the conjugate base of HCl and the conjugate acid of IN minus, which is HIN1. Now, HCl is a strong acid, strong. So this reaction goes to completion. That's why we have this one-way arrow here. Yes? Remember, once HCl has given away all its protons, chloride is too weak to take them back. I don't know if you remember this when we were in the class. At one point, I played hydrochloric acid and I tried to take a proton back and I just couldn't do it. I was too weak. I also spent a lot of time running away because that was kind of fun, but mainly I was just too weak to take that proton back. So you will not have this happening here. Okay, that does not happen. No. Okay, so you actually don't end up with any HCl and IN minus. So the only thing we're going to have at the end of this reaction, these guys here get all used up. And so all we have left at the end is those guys. So all that's present in that little well, that's like the spot on the spot plate, okay, the well. I drew a circle, it doesn't look like a spot plate, it's not on a plate, there we go. All we have left is Cl minus, and we have HIN1. Chloride is colorless. You've seen salt water, it is not colored. NaCl water, not colored. When we go back and we look what happened, this turned our system red. So, huge, terribly difficult question here. What color is HIN1? It must be red. Yes. Okay, so this turned our indicator red. All we have left is HIN1. So which species is red? It's the HIN1. Okay, and so that gives us the color of the indicator. So if you put hydrochloric acid with an indicator, the indicator will take on its acid form color. Okay. Now we did the opposite. We took a base, NaOH, and we also put it with HIN1, and it turned yellow. Okay, so NaOH is a base. It has to react with an acid. So it has to react with the acid form HIN1, which is why we put HIN1 in the reactants. It's a neutralization reaction. We end up with a salt and water. Okay, we had an acid. No, not an acid. We had a base plus an acid, giving us a salt plus water. If we write the net ionic form of this and ignore the sodium because it's a spectator, we just get OH minus. We have HIN1, which if you recall is red. We just determined that. And we have IN1 minus. NaOH is a strong base. Once it takes a proton away from the HIN1, it will not give it back. Okay, the proton is now stuck on water till the day it dies. I don't want red there because red is like saying it's red. Water is not red, not unless you put food coloring in it. Okay, goes to completion. Where was I going with this? Completion. So the only things that are going to be present are those guys. As it goes to completion, these guys are all gone. So all we have left is IN minus and H2O, and of course we know H2O is colorless. Well, so this will let us know what color IN minus is. And This turned yellow, so we have determined that the color of IN minus must be yellow. So which species is yellow? That would be our IN minus. So really the HCl and the NaOH are just there to let us know what color is the acid form, and we'll get the acid form when we put it with hydrochloric acid. Okay, so that's going to tell us the color of the acid form. And that's when we put it with a strong acid. So the strong acid shows the color of the acid form of the indicator. A strong base I wrote strong a base. Oh dear. A strong base shows the, I should say IN1, not I1. A strong base shows the base color of the indicator. Base color of base form of the indicator. Okay. So that's why we use the HCl and the NaOH. Those strong ones will tell us the colors of the various forms. Now we're going to get into those weak acids, and we might find that HA1 is stronger than HIN1. We might find that HA1 is weaker than HIN1. But we're going to use our results to let us determine that. You might even just be able to look at this and go, wow, HA1 turned HIN1 red. Anyone tell me who is the stronger acid just by looking at that and thinking about what we just did? Is the stronger acid HA1 or HIN1? Don't worry if you can't. We're going to go through like in gory detail how to figure it out. Any guesses? I'll give you a minute to think. Okay, I got one guess. You're right. Yay, it is HA1. It may be that that's all you need, right? You can see that that's what's happening and you go, oh yeah, it's HA1, but we're going to go through in gory detail how you can figure it out if you need to. If you don't want to listen to the rest of this and you just want to go ahead and start on the worksheet, you could do that too. That would also be great, but I'm going to go through this. So here we are. We have the acid is always reacting with a base. So when we have HA1, it has to be reacting with the base form of the indicator, HIN1. We could, if we wanted to, write the reaction the other way round, where we have HIN1 acting as the acid, and that should say A1 acting as the base. However, oh, and this is backwards. This is all backwards. Oh my God. Oh, okay. This should say IN minus, and that should say HA1. Sorry about that. Okay, so even though we could write it either this way or this way, those two reactions are just the opposites of one another. The reactants have been flipped to the products and vice versa. So it doesn't matter which one we use. So I'm going to choose this one here because it looks the most like our HCl reaction. You can see that we've got our HA1 is taking the place of HCl in that reaction. The only other thing that's different other than the species is that we know that HCl is a one-way arrow, and we know that HA1 being weak and HIN1 being weak, we have an equilibrium arrow. All right, page turn. Oh, awkward. There we go. Okay, so if you didn't get there on your own, here we are. We have HA1 plus HIN1 is red. Well, we know that HCl also made it turn red, and we know that we don't have any reactant left, which meant that the HIN1 was our red species. And if we are also seeing red, then that means that we must be seeing mostly HIN1, which means our predominant species. What does predominant mean again? Predominant means main. Yes, predominant means main. So the main species present in HCl plus IN plus the indicator is the HIN1, not the IN minus. Oh, I should have written in red. I write it in red. HIN1. And because we're seeing that same color, that red, that means that our predominant species in the reaction of HA1 with the indicator, we are also mainly seeing HIN1 and not very much of the yellow IN1 minus. We don't really see that yellow color there. Okay, so because it's mostly red. So we're shifted way, way, way to the right. So which side is favored, products or reactants? Products. Yay. Products. And if the products are favored, this is going back to some Bronsted-Lowry strength here. If the products are favored, then which acid is the stronger weak acid? So now we're looking at our two weak acids, HA1 and HIN1, and we are asking which one of those is stronger. If we favor the products, that means products must contain the stronger or weaker one. If products are favored, stronger or weaker acid. If products are favored, products have to contain the weaker acid. Yes, the weaker side is always favored. Okay, so in a Bronsted-Lowry acid-base equilibrium, the side with the weaker acid and the weaker base is favored. The stronger acid is better at giving away its protons, so it spends more time in its weaker conjugate base form. Okay. Now, another way to think about this, if you're solving a problem like this in a lab, is that we have HCl, which is a strong acid. HIN1 is an indicator, therefore it must be a weak acid. Therefore, we know HCl is stronger than the indicator acid form. If HA turns the indicator the same color as HCl, which is a strong acid, then HA must be stronger must also be the stronger acid because it is behaving in the same way as a strong acid did. So you can make, if the colors are the same, then these are both stronger than the indicator. So we can fill this in on our table. Here we go. We can say that hydrochloric acid is stronger than the indicator. And what's happening here is we're saying, okay, this is stronger than that. Okay, HCl is stronger than HIN1. We can do the same thing for HA1. We can say that HA1 is stronger than HA1 is stronger than HIN1. So that's how you would put that in a table to sort of organize it a little bit. Okay, and on the next page we have, oh, what do we have? HA2. Okay, I'm not going to go through like the whole thing. If you want to look it up on the in the filled in copy, you can, but it's pretty straightforward, I think. We have HA2 with the indicator is yellow. So tell me, and what color, who turned the indicator yellow? HCl or NaOH? This was the same color as the NaOH. And it's a different color than the HCl. So HA2, is it stronger or weaker than HIN2? Or IN1 rather? HA2, stronger or weaker than HIN1? Hello. It's doing something different than HCl. Okay, it's weaker. If we're not seeing that, okay, I will go through the whole thing unless if you all type in, I get it, I just don't want to say anything. Or if you just type, I get it. But I will go through this. Okay, so when we put the HCl with the indicator, we got a result of red. Okay, and remember our HIN was red. When we put the indicator in with the HA2, we saw the result of yellow, which means that we are seeing the yellow species, which is the IN1 minus. So the predominant species with HCl is the HIN, okay? Out of our two choices, HIN versus IN minus. HA2, on the other hand, we mostly see the yellow color, the IN minus, so that is our predominant species. So which side of the reaction is favored? Well, we're seeing that yellow color, so our reactants are favored. And if the reactants are favored, then who is the stronger weak acid? So this side over here is favored. And if it's favored, what kind of acid and base do we have on this side, weaker or stronger? If it's favored, these guys must be weaker, and these guys must be stronger. Okay. So that means that out of our two acids, I need a different color here. Oh, green, that'll do. Here's acid 1, here's acid 2. Out of those two acids, HIN1 is stronger than HA2. So HA2 is the weaker of those two acids. HIN1 is the stronger of those two acids. So let's put them in a table. Here we go. Once again, we still have our HCl is stronger than the HIN1. The HA1 is stronger than the HIN1, but the HA2 is weaker than. So this is the weaker end is pointing at the HA2, and the stronger end is pointing at the HIN1. Okay. So looking at our conclusions so far, can you tell if HA3 is stronger or weaker than HIN1? Is HA3 stronger or weaker than HIN1? Yes, HA3 is weaker. It is doing the same thing as the NaOH did. It is doing the opposite of what the hydrochloric acid did. So hydrochloric acid is stronger than the indicator. HA3, because it's doing the opposite, must be weaker than the indicator. So when compared with HCl, HA3 turns HIN1 a different color. And therefore, if it is different, then HA3 has to be weaker because HCl was stronger and HA3 is doing something different than HCl. So it must be a different relative strength. Can you fill in the rest of the table? Would you like 5 minutes to fill in the table? Or would you like me to just scroll to the next page and keep going? Keep going. Okay. So here we filled in the table. If you want to, you can go back and see if you can fill it in successfully and make this happen. All right. So out of the 3 weak acids, now we have all our greater thans and less thans filled in. How can we tell which of HA1, HA2, and HA3 is the strongest? And how can we tell which is the weakest? Well, we can look at this and we can say HA1, when we're comparing it with HIN1, HA1 is stronger than HIN1. So HA1 is stronger than HIN1. HA1 is also stronger than HIN2. And it is also, oh my gosh, look at this, stronger than HIN3. Okay. HA2, pen here, maybe a blue pen, that'll do. Okay, HA2 is weaker than HIN1, so we cannot put it in as stronger. It is stronger than HIN2, so it's stronger than HIN2, and it is also stronger than, come back here, there we go, HIN3. And finally, we go to our HA3, which is weaker than indicator 1. It is weaker than indicator 2, and it is only stronger than indicator 3. H3. So, who out of HA1, HA2, and HA3 is the strongest acid? HA1, because it's stronger than all 3 of the indicators. So that's HA1, stronger than all 3 of the indicators. Who is the weakest of the weak acids? Who's the weakest of the weak acids? HA3. HA3, because it is stronger than only 1 of the indicators. So this is stronger than 3, this is stronger than 2, this is stronger than only 1. So if we were to write our acids in order, we would say that HA1 is stronger than HA2 is stronger than HA3. And I'm really disappointed that I put them in order so that it goes 1, 2, 3. I'm going to have to change this worksheet to fix it up, but I could not get it completed in time and change it. After I figured out what I'd done, I was like, no. Okay, we're going to do the same thing for our indicators. And in this case, we're not going to be looking across the row. We're going to be looking down the column. So in this case, we can see that HIN1 is stronger than HA2, and it is stronger than HA3, but it is weaker than HA1. Okay, so for things that HIN1 is stronger than, HIN1 is stronger than HA2 and HA3. HA2 and HA3. HIN2. Who is HIN2 stronger than? Who is HIN2 stronger than out of our 3 weak acids? Only HA3, that's right. Okay, there we go. The other ones is weaker. All right, so HA3. And who is HIN3 stronger than? Who is HIN3 stronger than? None of them. Okay, it's weaker than everybody over here. Okay, so none. So out of those 3, hopefully it's pretty straightforward to see that HIN1 is the strongest because it is stronger than 2 of the weak acids. That's compared with only 1 for HIN2. And then, of course, we have HIN3 is the weakest because it's only stronger than, none of the weak acids. So the order of the indicators is HIN1 is stronger than HIN2 is stronger than HIN3, which is why I say this made me really sad because it was 1, 2, 3, and now it's 1, 2, 3. Ugh, drives me crazy. But that's okay. Now we're going to take our 2 lists. Strongest HA1, HA2, HA3, HIN1, HIN2, HIN3, and now we're going to try and slot them together. You can't see it, but I'm like interlacing my fingers. So we're going to try and figure out, does HA1 go up here or does HA1 go down here? Okay, so let's take a look at our chart and say, is HA1 above HIN1 or is it below HIN1? So here we go. Now I've scribbled all over this so badly. HA1 is stronger than HIN1, so it's going to slot in above. Okay, so if we put it in, we would have HA1 slotting in above. And we could do the same thing for HA2. We will actually find that it is stronger than HIN2 if we check our chart, HA2, and then HA3 is actually stronger than HIN3, so we get HA3. So our list of acids then is HA1, HIN1, HA2, HIN2, HA3, HIN3. And like I said, 1, 2, 3. It's just too tidy. I don't like it, but that's okay, because it probably means that we finished maybe a little quicker than we otherwise would have. And I really wanted to be done within an hour. Is it still an hour? I've lost my clock. Oh, it's 1 o'clock. Oh my God, we're done. Not bad. Okay, so homework, do 5.2b. Okay, and I will see you guys tomorrow. Thank you for showing up. Hopefully you're going to go out and enjoy some of that snow. It's beautiful. Have a great day. You guys are the best. Okay, stop. Did I start recording again? No. Did I start recording? I think I did. Yes, I did. Yeah, I did.